Lesson: Convolutional Neural Networks, CNNs, in Image Analysis. Convolutional neural networks have revolutionized the field of image analysis, offering efficient and effective approaches to tackle complex computer vision tasks. At the heart of CNNs lies a design inspired by the human visual cortex, functioning to automatically and adaptively learn spatial hierarchies of features from images. This ability to automatically extract and understand intricate patterns has positioned CNNs as a cornerstone in computer vision applications, from facial recognition to autonomous vehicle navigation. CNNs operate through a series of convolutional layers, pooling layers, and fully connected layers. Convolutional layers apply a set of filters to input data, capturing spatial features such as edges, textures, and shapes. These filters slide over input images to produce feature maps that highlight specific patterns. Pooling layers then reduce the dimensionality of these feature maps, preserving essential information while minimizing computational load. Finally, fully connected layers interpret these features to classify or regress outputs, completing the neural network's learning process. The practical implementation of CNNs in image analysis often involves leveraging popular deep learning frameworks such as TensorFlow and PyTorch. These frameworks provide user-friendly APIs and extensive libraries to streamline the development of CNN models. For instance, TensorFlow's Keras API simplifies the creation of CNN architectures, allowing professionals to define layers, compile models, and train networks with minimal coding effort. PyTorch, on the other hand, offers dynamic computational graphs, which are particularly beneficial for researchers experimenting with novel network architectures. Consider a practical example in medical imaging, where CNNs significantly enhance diagnostic accuracy. In tasks such as tumor detection in radiological images, CNNs outperform traditional image processing techniques by identifying subtle patterns that may be indicative of malignancies. This improvement is largely due to CNN's ability to learn from large datasets, capturing complex features without manual intervention. By deploying pre-trained models like VGGNet or ResNet, professionals can further refine these networks to suit specific medical imaging tasks, often employing transfer learning to expedite the process and reduce the need for extensive labeled data. Another compelling application of CNNs is in the realm of autonomous vehicles, where real-time image analysis is critical for navigation and safety. CNNs are employed to process input from cameras mounted on vehicles, identifying and classifying objects such as pedestrians, other vehicles, and traffic signs. By integrating CNNs with reinforcement learning frameworks, developers can optimize vehicle control systems to improve decision-making in dynamic environments. This integration exemplifies how CNNs can be adapted and extended through various AI techniques to enhance functionality and reliability in real-world applications. While CNNs offer powerful solutions, they also present challenges, particularly in terms of computational demands and interpretability. Training CNNs requires significant processing power, often necessitating the use of specialized hardware such as GPUs. Tools like NVIDIA's CUDA and QDNN libraries are instrumental in accelerating CNN training by optimizing parallel computations. Additionally, cloud-based platforms like Google Cloud AI and AWS SageMaker provide scalable resources, enabling professionals to train and deploy CNN models without investing in costly infrastructure. Interpretability remains a critical concern, as CNNs are often perceived as black boxes, making it difficult to comprehend how they arrive at specific conclusions. Techniques such as GradCam have been developed to address this issue, providing visual explanations of CNN predictions by highlighting areas in input images that influence the output most. These insights are particularly valuable in sensitive domains such as healthcare, where understanding the rationale behind a model's decision is crucial for clinical validation and trust. Moreover, the robustness of CNNs against adversarial attacks poses another challenge. Adversarial examples input images perturbed with subtle noise can drastically alter CNN predictions, raising concerns about model reliability. Researchers have proposed various defense strategies, such as adversarial training and defensive distillation, to enhance CNN robustness. These approaches involve training models on adversarial examples or modifying network architectures to resist perturbations, thereby bolstering model security. Real-world deployment of CNNs also necessitates careful consideration of ethical and privacy implications, particularly when dealing with sensitive data like personal photographs or medical records. Ensuring data anonymization and compliance with regulations such as GDPR is paramount to protect individuals' privacy. Additionally, bias in training data can lead to biased CNN models, underscoring the importance of data diversity and fairness in model development. Techniques like data augmentation and synthetic data generation can help mitigate bias by enriching training datasets and promoting model generalizability. To illustrate the transformative impact of CNNs in image analysis, consider the case of facial recognition technology. CNNs have dramatically improved the accuracy and speed of facial recognition systems, enabling applications from smartphone security to law enforcement. These systems leverage CNN's ability to discern intricate facial features and expressions, often achieving recognition rates exceeding human capability. However, the deployment of facial recognition technology also raises ethical concerns, such as surveillance and individual rights, which necessitate ongoing discourse and regulatory oversight. In conclusion, convolutional neural networks have become indispensable tools in the domain of image analysis, driving advancements across diverse sectors. By leveraging frameworks such as TensorFlow and PyTorch, professionals can effectively implement CNNs to address real-world challenges, from medical diagnostics to autonomous navigation. Despite their immense potential, CNNs also present challenges, including computational demands, interpretability issues, adversarial vulnerabilities, and ethical considerations. Addressing these challenges requires a multifaceted approach, encompassing technical solutions, ethical awareness, and regulatory compliance. As the field of computer vision continues to evolve, CNNs will undoubtedly remain at the forefront, offering innovative solutions and reshaping the landscape of image analysis.